Alright, hey everybody. We're going to try to continue where we left off yesterday and talk a little bit more about parametric equations. Today we're actually going to try to focus first on arc length, and if I have time I'm going to focus on speed, but I have a feeling that arc length may take up this whole video. So if you remember, we've done arc length before when we had a function of x. And, we had an integral of the square root of 1 plus the derivative squared from a to b dx. That this is the this is the arc length of our function from a to b. Well, when we're dealing with parametric equations, remember we're dealing with equations where our position in both x and y is defined by the variable time. So in this case, we're going to need a different equation. It'll look similar-ish, but not exactly the same. So our equation for parametrics is the integral from a to b of the square root, and then we will have two things squared on the inside, and dt. This may make some sense to some of you. If you think about it, we're dealing with two different things that are changing here. Remember, we're dealing with an x change and a y change. So to find our arc length, we're going to have to take the derivative of the x, square it, add it to the derivative of the y squared, take the square root, and integrate all of that from a to b. And unlike the equation that we had for just a function of x, there are many more instances where this actually turns out something that we can actually compute by hand. So let me see if I can, while this is still rolling, kind of get us back into working a problem. Okay, so we're going to work a problem real quick. We're going to see if we can't find the arc length of x of t being t cubed and y of t being 3t squared over 2. And we want to do this, let's say, on the interval from where t is going from 0 to root 3. Okay. So we're trying to find the length of this whole particle. So to do so, let's see if we can bust out our little formula here. We're talking about going from 0 to root 3 of the square root of the derivative of this thing squared, 3t squared, plus the derivative of that squared, or 3t dt. And I hope many of you will see that we can kind of simplify this a little bit. 9t to the 4th plus 9t squared. And then some of you may see that we can actually factor a 9t squared out, which then we could square root that to get a 3t on the outside, leaving me with t squared plus 1 on the inside. And once we get to here, inside the square root we have a quadratic. Outside the square root we have a linear thing. This looks like something that we might be able to do a u substitution for. So over here to the side, I'm going to let my u be t squared plus 1. My du then will become 2t dt, which is very close to my 3t dt. I'm going to pretend like this 3 is already on the outside of that integral, and I'm going to say 1/2 du is t dt, and then I'm going to start my substitution. So I have 3/2. The integral from when I put 0 into my u equation I get 1. I'm going to put root 3 into there. I get 4. And I'm going to end up with the square root of u du. And when I integrate this, I'll have 3 halves times, it'll be u to the 3 halves times 2 thirds, which is kind of convenient going from 1 to 4, since that will kind of just turn into u to the 3 halves from 4 to 1, or from 1 to 4, excuse me. When I put 4 into here, I'm going to get 8, and when I put 1 into here, I'm going to get 1, which is going to give me a final answer of 7. So our first problem, the arc length, when our x position is defined by t cubed and our y position is defined by 3t squared over 2, going from a time starting at 0 and ending at square root 3, we're going to end up with a answer of 7. Okay, so let's look at our next problem here. We're going to look at our next problem trying to find the arc length of this parametric equation on this time interval. So we'll set it up much in the same way we set the last problem. We're going from 0 to pi over 2 this time, of the square root of, and here comes the fun part. I actually need the derivatives of x of t and y of t, so let's put them off to the side. Alright, the derivative of x of t is going to be 3 cosine squared of t times a negative sine of t, and y prime of t is going to be 3 sine squared of t times a cosine of t. Okay, and then we're going to go in and we're going to square all this. So this is, where the fun begins, I guess you could say. So when I square that x prime of t over there, that's going to leave me with 9 sine squared t cosine to the 4th. And that's both of those are t's in there. I know those are kind of like pluses. Plus, I'm going to square the y of t part, and it's also going to give me 9. This time I'll have sine to the 4th t cosine squared t. Alright, so again, I see that there's some things that I can get out of here. Looks to me like I can get the 9, a sine squared, and a cosine squared factored all out. So I'll go ahead and get the square root of all that. Whoa. And that would be 3 sine of t cosine of t. And what would be left inside our square root would be 2 cosines and a sine squared. And I've got my dt back here. Math police were coming to get me at this exact moment. But you can see here we have one of our trig identities. Sine squared plus cosine squared, our old friend. Oh, what a lovely day it is. So that's going to go to 1. Alright, and we're just going to end up with the integral from 0 to pi over 2. I'll factor the 3 out of sine of t cosine of t dt. Okay, so 3 sine t cosine t dt integrated from 0 to pi over 2. We can use a u substitution on this, which I can already feel the excitement. Okay, so let's see. U is equal to sine of t, and so du is cosine of t dt. So this over here is 3 times the integral from 0 to pi over 2 of u du. So we end up with 3 halves u squared going from 0 to pi over 2. Oh, excuse me, shouldn't be going from 0 to pi over 2 anymore. I should be putting 0 in the sign. That still gives me 0. Pi of 2 in for sign. That gives me 1. And so this is going to give me 3 halves minus 0, which is in fact 3 halves. Whoop-de-doo, we did it. Congratulations, us. So what I'm hoping you'll see with this is that finding the arc length of a parametric equation is just a matter of knowing the formula, sometimes doing a little bit of work inside the square root to kind of simplify things. If it's not something that we can in fact integrate, I will allow you to use your calculators on it. It'll be very explicit in the problem whether or not calculators are allowed or not allowed. So I don't think we should have any problems with this. And I will try to make another video in a little bit dealing with speed. So we're going to start talking about, if we're talking about things changing with respect to time, which these are positions with respect to time, we can start talking about speed in parametric as well.